Good morning. Today, I'd like to talk about work done by moving an object around in opposition to the force of gravity. To start with, I'll remind you how you did this in a very simple situation. We're going to have some object that has a certain mass to it, say 10 kilograms, and we're going to lift this 5 meters straight up and try to figure out how much work was done. The first thing that we need to be a little bit careful about is kilograms is a unit of mass. It's a measure of how much matter is present. Mass in metric units could be measured in kilograms, or in the British imperial units could be measured in slugs. We'll stay away from that as much as possible. Weight is a force. It's the response of the object due to gravity, the force due to gravity. In system international units, we would measure that in newtons, and in British units, in pounds. As I move this object around, its weight conceivably could change. We'll talk more about that in a moment, but the amount of matter in it doesn't. In the familiar situation, you say that work is force times distance. Newton's second law says, though, that force is mass times acceleration. In this case, the acceleration due to gravity. This is where the mass times acceleration due to gravity times distance that you moved formula comes from in elementary physics classes. As we're going to see shortly, this is not completely correct. In this particular case, though, I know the mass, I know the acceleration due to gravity, and I know the amount of change in position that we're going to have. Doing the arithmetic, we find out that 490 joules of work was done. Newton's inverse square law of gravitation says the gravitational force acting between two objects, that is, the force on this object caused by that object, or the force caused by the small object on this object, is given by a universal constant times the mass of the first object times the mass of the second object divided by the square of the distance center to center. If I use meters, kilograms, and seconds for my units, the g works out to be about 6.674 times 10 to the minus 11 power. For reasons that'll become clear in a moment, the mass of the Earth is about 5.972 times 10 to the 24 kilograms, and the radius of the Earth is 6.371 times 10 to the 6 meters. I want to recall Newton's second law again. That's the one that says force equals mass times acceleration. Specifically, I'm thinking about the force acting on this thing that I'm thinking of as the much smaller object. On the one hand, the force acting on this object is its mass multiplied by its acceleration. On the other hand, the force acting on that object is also the force due to gravity, g product of the masses divided by x squared. A remarkable thing happens if you'll notice that little m is a factor on both sides of this equation. I can divide the little m out and find out something very unusual. Specifically, I'm thinking about the force acting on this thing that I'm thinking of as the much smaller object. On the one hand, the force acting on this object is its mass multiplied by its acceleration. On the other hand, the force acting on that object is also the force due to gravity, g product of the masses divided by x squared. A remarkable thing happens if you'll notice that little m is a factor on both sides of this equation. I can divide the little m out and find out something very unusual. The acceleration of this upper object does not depend on its mass. As far as we know, gravity is the only kind of force that does something like that. Furthermore, if I were actually on the surface of the Earth, the acceleration due to gravity would be g times the mass of the Earth divided by the radius squared of the Earth, which is why I wanted to write all these numbers down over here. Putting the indicated numbers into this formula, I find out that at the surface of the Earth, what we usually call little g, the acceleration due to gravity, is about 9.81 meters per second squared. That's the origin of the often quoted 9.8 meters per second squared. There is something funny about this. The acceleration due to gravity depends on your position. X is the distance from the center of the Earth in this context. As long as you don't move around distances that are very large compared to the size of the Earth, this number won't change much. But if you move upwards large distances, the force due to gravity, and therefore the acceleration due to gravity, are going to get weaker. The force is not a constant, which means I can't calculate work just by saying force times distance any more than we could do it for springs. To illustrate what I'm talking about, imagine that I have an individual on the surface of the Earth. That means that the x will approximately be 6 times 10 to the 6 meters. Then he goes up to the top of a building of height h meters. I claim the acceleration due to gravity will be smaller at the top than it is at the bottom. Of course, you've never noticed that you weigh less at the top of a building than at the bottom, for some very good reasons that we'll look at right now. The derivative of the acceleration due to gravity with respect to position variable x is easy enough to calculate. If delta x is not very big compared to x, then delta a, the change in the acceleration, over the change in x is approximately equal to this derivative. For small changes in x, delta a is approximately negative 2 gm over x cubed times how much you changed the position. I can factor this up a little bit, though. If I notice that I can write gm over x cubed delta x as gm over x squared times delta x over x, and then I remember gm over x squared is the acceleration due to gravity, and delta x is the height of the building, the amount that the acceleration increases by is negative 2 acceleration due to gravity at the surface of the Earth times the height above the surface divided by the radius of the Earth. The minus sign indicates that the acceleration due to gravity has actually gotten smaller. If I assume that my building is 200 meters high, then I can simply put negative 2 times 9.81 times 200 divided by 6 times 10 to the 6, and when the dust settles, the acceleration due to gravity has decreased by an amount 0.000654 meters per second squared. Since it started off being 9.8, this change is very tiny compared to the actual value of the acceleration. You would need to have extremely high precision measuring instruments to detect this. That's why, for many purposes, we can pretend that the force due to gravity, also the acceleration due to gravity, is a constant. If we start moving objects around at distances that are comparable to the radius of the Earth, that's no longer going to be true, and our mass times g times h formula is no good. My microphone had some sort of audio dropout problem and didn't record the rest of my video. So I'm doing this with an external mic. It'll be interesting to see how the sound quality varies from the way I was doing it before to now. In any case, if the masses of the objects don't change, then I can treat the top of the fraction gmm as a constant. My force law now reads F is a constant divided by x squared, which is very reminiscent of Hooke's law, which was force equals constant times x. Imagine that you have an object that on the surface of the Earth weighs 100 pounds. That object is lifted upwards by 3,000 miles. Since the radius of the Earth is about 4,000 miles, my x value goes from 4,000 to 4,000 plus 3,000, or 7,000 miles. If I do the calculations using this information, my work will come out in mile pounds. That's kind of a strange unit of measurement, but since we know that there are 5,280 feet in a mile, we'll be able to convert that into feet easily enough. As with Hooke's law, the statement that when you're on the surface of the Earth, the object weighs a certain amount allows you to figure out what the k is. I'm going to leave the k in that form. It's just a number, because we already know on general principles that I should calculate the integral of the force with respect to position, and since we know the beginning and ending locations, it's direct to write down the integral from 4,000 to 7,000 of the constant k over x squared. Even though constant k is a rather large number, it's just a constant. Doing the integral, I find out how many mile pounds of work is needed, and as I said, each mile consists of 5,280 feet, so multiplying this result by 5,280 will give me the number of foot-pounds. There are a variety of other situations involving gravity. One of them involves something called escape velocity. I may do a small separate video on that topic, but as for today, I believe this is all I'm going to talk about. I hope everyone has a good day. I'll talk to you again soon.